AB Calculus, Section 3.1, Introducing the Derivative. Objectives for this video are tangent lines, as well as rates of change, instantaneous versus average rate of change, which we've talked about, equations of tangent lines, and slope of a curve. All of those topics are very closely related, so we're going to kind of work through them, some simultaneously and sometimes separately. So let's look at the opener here. Given that m equals 3, that would be slope, and p equals, or p is the point negative 2 comma 5, write the equation of the line through p and the equation of the normal line through p. Okay, so p must be a point on a curve of some sort. So let's say p is on this curve f of x. Let's say that this is p. Okay, so this is the point p. So the tangent line has a slope of 3 and goes through the point negative 2 comma 5. So let's write an equation of the tangent line. So I would write the equation to be y minus 5 is equal to 3, x minus a negative 2, which I'll write as x plus 2. That's the equation of the tangent line. Okay, now how are a tangent line and a normal line related? Well, a normal line, also through p, is a line that forms a right angle with the tangent line. Therefore, it will be almost the exact same equation. It goes through the same point. However, the slopes are opposite reciprocals. So both equations go through the point negative 2, 5, but their slopes are opposite reciprocals. There is your normal line. Okay, let's continue with average rates of change, a ratio of two changes. So the average rate of change we've talked about can be written in two forms. Okay, it can be f of x minus f of a over x minus a, or it can be f of x plus h minus f of x over x plus h minus x, which ends up equaling h. So really we have a change in one variable, right? So this would be our change in y over our change in x. And that's all that an average rate of change is. But in order to calculate the average rate of change, you need 2 points. So for example, in number 1, average speed would be change in position over change in time. Average growth rates for population would be population change and change in time. And an average monthly rainfall would be change in inches of rain over changes in months or number of months. So as we've seen, and we've covered this before, this should be review at this point. The average rate of change is the slope of the secant line through 2 points on a curve. So we've got this equation for the secant line, and we've also got, as we talked about earlier, the difference quotient. Oh, and it looks like it's right there. So I didn't even see it. All right, I'll just write it anyways. Okay, now how do we find the instantaneous rate of change? So the change in population at an exact moment in time, not necessarily over an interval of time, but at an exact moment. What we do is we can either take the average rate of change in the form f of x minus f of a over x minus a, or we can take the other form of the difference quotient, which is f of x plus h minus f of x over h, and we use limits. So we would take the limit as x approaches a in the first form, and the limit as h approaches 0 in the second form. That's how we will calculate the instantaneous rate of change when x, or the change in x, goes to 0. That will be the slope of the tangent line. All right, let's continue with some examples. Okay, example 1, find the slope of y equals x squared at the point 2, 4, and write the equation of the tangent line. Include a sketch. So the first thing that I really care about is I care about where the slope is taking place. It's going to take place at x equals 2. So what I want to do, in order to find the instantaneous rate of change of y equals x squared, what I want to do is I want to take the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so what is f of x? Well, f of x is x squared. F of x plus h is equal to x plus h quantity squared. We've seen this before. This is x squared plus 2xh plus h squared. So the limit as h approaches 0 of f of x plus h, which is x squared plus 2xh plus h squared, minus f of x, which is x squared, all over h, will simplify to, let's see, the x squareds reduce, combining like terms. I will factor out an h, giving me 2x plus h over h, which will, of course, reduce to the limit as h approaches 0 of the expression 2x plus h. Well, that comes out to be 2x. That means that the instantaneous rate of change, instantaneous rate of change, also known as the slope of y equals x squared, is equivalent to 2 times whatever the x value is. That is awesome. So the slope of the tangent line through the point 24 will equal 2 times 2. So the slope of that tangent line will be 4. Thus, I can write an equation of the tangent line. So the tangent line equation will be as follows. I've got a slope. That slope is 4. I've got a point. That point is 2, 4. Therefore, the equation will be y minus 4 is equal to 4x minus 2. So if we look at the equation in graphical form, here's the point 2, 4. The equation of the tangent line would be this. Outstanding. Okay, what about where x equals c on the same curve? Okay, so all I'm going to do is I'm going to take the slope of the tangent line anywhere on the curve. So the slope is going to equal 2x. Well, when x equals c, that means the slope will be 2c. Okay, now I do need a point, so the tangent line equation will require a point. So the point here I would have would be f of c equals c squared. So my point would be c comma c squared, and my slope would be 2c. So the equation of the tangent line would be y minus c squared is equal to 2c x minus c. There's the equation of the tangent line where x equals c on that same curve. Okay, let's look at example 3. Find the equations for the tangents to the curve y equals x squared at -1/2, 1/4, and at 1, 1. Okay, so again, I can utilize my simplified difference quotient and the instantaneous rate of change to know that the slope anywhere on the curve will equal 2x. Okay, thus at the point -1 half 1/4, the slope of the tangent line at that point, -1 half 1/4, will equal 2 times -1 half. All right, so that slope will equal -1. Whereas the slope on the curve, the tangent line to the curve at the point 1, 1, will equal 2 times 1, which will equal 2. Now notice that I have a point now, and I have a slope in both scenarios. Therefore, I can write the tangent line equations for both in the form y minus 1/4 is equal to -1 x plus a half. That would be the tangent line to the curve going through -1 half 1/4. And the tangent line to the curve going through 1, 1 would be y minus 1 is equal to 2x minus 1. There are your two tangent line equations. If I were to sketch them, it would make sense that the first would have a negative slope, seeing that on this side of the curve, the slopes tangent to the curve will be negative. And on the other side of the curve, of course, this point was the point -1 half 1/4, not to scale. On the other side of the curve, obviously not perfect, at the point 1, 1, the slope clearly is positive and not to scale as well. Okay, let's continue with a few more examples. Okay, so in general, to find the slope of PQ, here's PQ. All right, connecting P and Q with a secant line. I would just find the average rate of change by finding the slope from P to Q. So for this given situation, let's say that this was P and F of P, nothing we haven't seen already, and Q, F of Q. The average rate of change would be F of Q minus F of P over Q minus P. All right, that's how we find the average rate of change. To find the instantaneous rate of change at, say, x equals c, of course, that would be different, right? We would take the limit as h approaches 0 of f of x plus h minus f of x over h. And of course, I could work that differently with the alternative form. Limit as x approaches c of f of x minus f of c over x minus c. That would be the derivative, or the slope of the tangent line at x equals c. Okay, let's look at a couple definitions down here, and then we'll move on to some more examples. The derivative gives us the value of the slope of the tangent line to a curve at any given point. So as we've seen, this notation now is new, but we've seen these definitions. F prime at x, this is f prime, that's how we say it, of x. That represents the slope of the tangent line, okay, given by the difference quotient while taking the limit as h goes to 0. The alternative definition can be seen in the same way. However, notice the difference. This is going to be f prime at a. That is the derivative, or the slope of the tangent line at x equals a. Notice I can use the first form. Okay, if I want f prime at a, there should be an a there. Instead of having an x there, I could plug in an a. And that would also give me the slope of the tangent line at x equals a. Let's see if we can apply that to an example here. Okay, so if f prime exists, we say that f has a derivative, or is differentiable at x. A function that is differentiable at every point of its domain is a differentiable function. So let's apply the definition and differentiate, which is a different word, synonym for find the derivative, okay, of f of x equals x squared plus 1. Okay, so we know that by definition, the derivative function is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so our derivative will be equal to the limit as h approaches 0. F of x plus h will be x plus h quantity squared plus 1 minus f of x, which is x squared plus 1 all over h. So the derivative function, which can be used to find the slope of the tangent line anywhere on a curve, will end up being the limit as h approaches 0, x squared plus 2xh plus h squared plus 1 minus x squared plus 1 all over h. All right, let's simplify this. Notice I'm carrying my notation along with me the entire way. I'm going to get some common or some like terms to cancel. And what we see we have left here, I'm going to factor out an h, so that'll be 2x plus h. And I've got an h in the denominator. I'm going to reduce that. Therefore, like we saw earlier, the derivative function for x squared plus 1 is exactly the same as the derivative function for x squared. It comes out when I evaluate this limit. Notice how I'm going to evaluate this. As h goes to 0, 2x plus h goes to 2x. So the derivative function, if f of x is equal to x squared plus 1, the slope anywhere on the curve is equivalent to 2x. It's awesome. Regardless of what x is, I can input it there and find the slope at that very given point. All right, let's look at example 5 and apply the definition, actually the alternate definition, to differentiate f of x equals square root of x. Okay, so the alternate definition, which tells us that f prime at a is equal to the limit as x approaches a of f of x minus f of a over x minus a. All right, so this is going to be the derivative at x equals a. Let's do a little work here. Plug in our function and evaluate at x and at a. So f of x is square root of x, f of a is square root of a over x minus a. Now you might have asked yourself in chapter 2, when am I ever going to use limits? Right now. Okay, we're going to use them right now. Now this can be done in two different ways. We could either use the conjugate method or we could use factor cancel method. And I'm actually going to use the factor cancel method here. But I guess I could show you both. Let's do the factor cancel method first. Factor cancel. And then we'll do the conjugate method in just a moment. Okay, so factor cancel method. F prime at a will equal the limit as x approaches a of, I'm going to factor the denominator. And you might ask, well, how can you factor x minus a? Well, it is the difference of two perfect squares. And the square root of x is the square root of x. And the square root of a is the square root of a. That's extremely groundbreaking. Now, when I factor this, notice like if I factored x squared minus 25, I would have x minus 5 and x plus 5. So I should have x minus square root of a and x plus square root of a. Notice what will happen here. We will reduce x minus, or root x minus root a reduces with root x minus root a. Therefore, f prime at a is equal to the limit as x approaches a of 1 over root x plus root a. Okay, so if x approaches a, I'm going to do a direct substitution and plug an x in, or excuse me, plug an a in for x. I'm going to plug an a in for x. That will give me 1 over root a plus root a, which is equivalent to 1 over 2 root a. So there is the slope function. It's called the derivative, located at a. So if I wanted the slope of square root of x at 10, that would be 1 over the square root of, 2 times the square root of 10. All right, let's use the conjugate method now. F prime at a will equal the limit as x approaches a. I'm going to multiply square root of x minus square root of a over x minus a, top and bottom, times the conjugate of the top. All right, and remember, multiplying by the conjugate is useful because you don't have to FOIL. You just multiply first and last because the outside and the inside terms will reduce. So I've got the limit as x approaches a. And what happens when I multiply square root of x times square root of x? I get x. And I multiply square root of a times the square root of a. I get a. And in the denominator, I've got x minus a and the square root of x plus the square root of a. So we see these two terms reduce in a very similar fashion. And I am left with f prime at a equal to the limit as x approaches a of 1 over square root of x plus square root of a. Now I'm not going to go through and write the rest of it, but you can see that if I evaluate that limit, I get the exact same slope function. Okay, let's continue on with the last slide for this video. Okay, the last slide, I'm not going to do a whole lot of writing. I just want to talk about notation. So these are all the different symbols that can be used for the derivative function. So y prime, that is pronounced y prime. It's nice and brief, doesn't name the independent variable, however. dy dx, this is called dy dx, or the derivative of y with respect to x. It names both variables and uses d for derivative. df dx, very similar. It's very similar to the previous. It emphasizes the function's name, right? So f d dx of f of x. This is telling you, not asking you, it's telling you to find the derivative of f at x. This emphasizes the idea that differentiation is an operation performed on f. Capital D subscript x is the derivative with respect to x. That's something you typically won't see in AP Calculus. You'd see that in multivariable. And f prime of x, a very, very familiar, seeing that we looked at it, and common expression or notation for the derivative f prime, or the derivative of f. It is important to remember that d dx is called an operator. It's telling you to perform an operation. All right, everyone, that's 3.1. We'll see you in the next video.